Sometimes, when physicists seek experimental evidence for yet unproven theories, they turn to high-energy collisions between particles, such as those happening in particle accelerators. However, some experiments require energies that exceed what we can achieve on Earth. That's when scientists turn to the vastness of space.
Ultra-high-energy cosmic rays are a type of radiation with 100 quintillion times the energy of visible light. They are produced by the mysterious celestial bodies and cosmic events. However, the current physics theory predicts that ultra-high-energy neutrinos should also be emitted alongside these cosmic rays.
Ultra-high-energy neutrinos are subatomic particles that indirectly arise from protons spit out by certain celestial bodies. These protons accelerate through the cosmos and react with light or plasma to produce pions, which in turn decay and produce neutrinos.
The balance between different types of neutrinos could give us information about the celestial bodies from which they originate. It would also help us understand how their parent protons are produced. Unfortunately, there was scarce proof such a high-energy neutrino exists.
The problem is that they are extremely rare and difficult to detect. Even if thousands of them flew straight towards the Earth, almost all would go right through without interacting with anything. That's why the IceCube Neutrino detector was built near the center of the South Pole.
IceCube was completed in 2011. It consists of a network of the 5,160 optical sensors embedded into a large portion of the ice, weighing about 1 billion tons. IceCube's purpose is to detect faint ultraviolet light called Cherenkov light, which is an evidence that the high-energy neutrino collide with Earth.
Chiba University's International Center for Hadron Astrophysics, or IceHab, has been the sole Japanese participant in the project since its inception. We have been working on calibration of IceCube photodetectors and made pioneering contributions to the search for ultra-high-energy cosmic neutrinos.
However, so far, few high-energy neutrinos have been detected.
In 2012, I discovered the first ultra-high-energy neutrino signal. It was first time in 25 years since the supernova 1987A that we captured such a high-energy neutrino from space.
Afterwards, we set up a system to send real-time alerts of cosmic neutrino detections to astronomical researchers around the world. With this system, we've helped discover radiating objects through follow-up observations right after neutrino detection.
In 2017, we detected ultra-high-energy neutrinos that prompted the rapid follow-up observations. Its source was found to be the blazar galaxy called the TXS 0506 056, over 4 billion light years away. It was the first time we identified the hometown of the high-energy neutrinos and the ultra-high-energy cosmic rays.
The story did not end there, as another discovery was coming. Researchers needed a way to tell between the different types of neutrinos arriving from space. They suspected part of the answer lay in a theoretical mechanism for neutrino interactions predicted by Dr. Sheldon Glashow in 1959, now known as Glashow resonance.
Sheldon Glashow predicted the resonance formation of a double boson during the interaction of a high-energy electron antineutrino with an electron. The resonance requires a neutrino energy of 6.3 PeV, which is too high for human-made accelerators, and not into IceCube could we have probed it.
In 2016, the IceCube team received a pleasant surprise as an ultra-high-energy anti-electron neutrino was detected.
So I was working on a new search to look for high-energy neutrinos and luckily saw the 2016 event. After checking carefully, we concluded the event shows a unique signature It lighthouses and is consistent with expectations of W boson decay via glacier resonance.
Recent upgrades made to IceCube have enabled it to distinguish between neutrinos and antineutrinos, as well as between different types of neutrinos: electron, tau, and muon.
Understanding the differences between these neutrinos and detecting more ultra-high-energy events with IceCube will help us unveil mysteries in both the cosmic and subatomic scales.
We have our eyes set on the future, which is IceCube Gen 2. We plan on expanding the current facility by over 8 times.